Okay, so today we're going to start talking about Verilog HDL. HDL stands for Hardware Description Language. What it is really, hold on. Gamini, are we recording? Yeah? All right. What it is really, Hardware Description Language, you can think about it as if it's a programming language for hardware. Now, I know, and I mentioned a few times before, usually we have classes of those that really like programming and those that couldn't program if their life depended on it. And it's usually the case that those people who are not in the lectures are those that couldn't program if their life depended on it. So hopefully most of you will get what we're going through today. The idea behind a hardware description language in general is the fact that when we want to design complex system or complex circuits, then you can't just open our schematic editor like you do in your lab and then start putting AND and OR gates and start designing everything from scratch. It works really well for smaller systems, sort of the stuff that we're doing in the lab. But once you want to start designing really complex stuff, you won't sit there with your equations and do all of this. This is what we have CAD tools for. So the idea is that we can sort of program a hardware by writing out the description of what this hardware needs to do and let the compiler and the synthesizers do the hard work for us to figure out what's going on. Now, there's a huge difference between HDLs in general. HDLs, again, hardware description languages. There's a few of them out there on the market. We're going to talk about the Verilog HDL. I will mention VHDL, which is another one. There's a couple of others as well. But what's in common for all those HDLs is that distinguish them from regular programming languages is that when you write a program, say in C or any other programming language, your commands are executed one after the other, sort of in a serious manner. So you execute one instruction, you finish processing it, you move on to the next one. Obviously, when you want to program hardware, that's not quite the case. When we program hardware, we have to remember that we're programming a parallel structure. If you want to imagine it as a real scenario, imagine that you have few AND gates on your schematic or in your circuit. Then you evaluate the results of those AND gates continuously in time, and all of them are being evaluated all the time in parallel. You don't evaluate one of them, then you stop that, and you go to the next one, and then you go to the next one. And this is something that a lot of people tend to forget or not actually fully understand it when they come to program with HDLs. And this is a point where I'm going to try and emphasize again and again and again that what you program in Verilog, or HDLs in general, is always a parallel programming. Everything is being executed all the time at the same time. I will introduce to you some sequential commands in Verilog. We'll talk about it on Tuesday, which then it will look like C, and there's special structures for it in Verilog. But everything we will talk about today is all in parallel. Now, this point here that hardware description languages allow the designer to design complex digital systems, different levels of abstractions, then you can be as high level or as low level as you wish. You can either program the subsystems in the gate level, or you can program the behavior of your circuit by describing what you want the circuit to do, obviously in the programming language that I'll show you, and then let the compiler synthesizer figure it all out. So you can choose what level you want to program in. Now, essentially, there's two main ways to describe any design. Either the structural description. Structural description means we're actually writing out all the gates and the wires that are going to be in the circuit. So we're saying in the structural description, we will say, all right, I want to have 3 AND gates, and these AND gates will be connected to this OR gate with these wires, and this will give us the output that's that. So that's a structural description, which is literally writing out the design of the circuit. Other than that, there's a data flow description, which lets you describe what you want the circuit to do, again, in the Verilog language or in the HDL language, and let the synthesizer figure out how to implement this. These are just, I've got a couple of slides explaining, again, about the structure and the data flow. Set this. So we're listing all the components, all the gates, the wires, input and outputs, and we tell it how to connect them. This is known as a netlist. You might see this term both in this course, maybe in other electrical courses. You might have seen it in the lab. A netlist is pretty much a list of all the components, all the wires, and the connections between them. That pretty much tells you how you, that describes a whole circuit that you can then take and, to another computer, to another system, and then let that new system actually implement it for you. Components can either be primitives or more complex functions. The idea is that you can either use those low-level gates, the AND or NOT gates that we've learned, or you can design your own modules, and this is something we'll see now, and then enclose them in those black boxes, and then use them as a component. For example, you might design your own decoder, and then enclose it in a module, or if you can, if you want to think about it, in a black box, and then instantiate this decoder and say, I want to use this decoder, these are the inputs, these are the outputs. And then you can sort of build up on top of smaller subsystems that you build. So that's all in the structural description. The data flow description, also known as the behavioral description, is a functional description of the unit. You tell it what you want to do, so you can describe things like Boolean equations, truth tables, and even arithmetics. You don't actually have to build the circuits that do the arithmetics for you. And we will learn about arithmetic circuits in week 9, by the way. And then let Verilog or your CAD tools figure out how it's all being implemented. One last point, the two descriptions, so, whoops. Don't tell me it's going to crash. When it thinks too much, I knew it. Just restart. When you have structural, come on, there we go. Structural and data flow, you can mix them together. You can have a little bit of structural, a little bit of data flow. You don't have to choose one or the other. Now, when we work with HDLs, most HDLs, not necessarily just Verilog, we have few main components or tools that will be there for you to use. You probably have seen most of them in the lab. Your Xilinx ISC tool is actually a synthesis tool. It's a design tool, and it gives you all these different functions. You have your text editor, which is where you write your program. Usually, in dedicated text editors for HDLs, you'll have something that highlights the keywords, highlights the syntaxes, might even warn you if you're doing something wrong as you go along. You have a compiler that will take your, your text description, your program, and it will parse through it. You will understand what you're trying to do. It will tell you if there's any syntax errors that you might fix. And then it compiles it into some intermediate file that's not actually technology related. So it doesn't matter where you're going to actually implement your circuit on, whether it's an FPGA or a dedicated chip. This will be this intermediate language that will be later read by the synthesizer. The synthesizer will take your intermediate language file, and this will actually implement those synthesizers on your specific technology that you're going to use. So in the lab, we're using FPGAs. Our synthesizers actually maps and routes all the components dedicated to that specific FPGA that you're using. But if you choose another FPGA type, or if you choose a dedicated chip, the result from the synthesizer will be different. Now, the last thing, which is a really important part of design tools, is the simulator. Before you actually go and implement things, you want to simulate to see that it does what you want. It's okay with FPGAs because you download it. If something doesn't work, that's all right. Not so great when you design an actual chip that you send to the manufacturers. Takes about a year to actually get your chip back, and then you go, oops. So you have to do some really heavy simulations and some really heavy testings before you actually send it out for production. Now I said there's a few different hardware description languages out there. We will concentrate on Verilog. And I lost my pen. In this course, we'll concentrate on Verilog. There's another main player out there, which is VHDL. Verilog and VHDL are two of the main languages out there in the real world when you design things. All the other little players, you see them every once in a while, not so much. There's about 50-50 split between VHDL and Verilog. Now, the question is, which one's better? Why do we learn one and not the other? Well, first of all, there's always an argument which one's better. Both of them pretty much do the same thing. Both of them have two different syntaxes. So what I'll teach you today is the Verilog. VHDL looks completely different, but essentially it does the same thing. It's a hardware description language. Why are we doing Verilog and not VHDL? Because I said so. It's as simple as that. It comes down to personal preference. I personally find Verilog to be easier to understand and work with. I'll show you as we go along some examples of what VHDL, not too many examples, but I'll tell you why I prefer Verilog over VHDL. Just so you know, Verilog is very similar to C language. This is partially the reason why I actually chose us to do Verilog. You will, if you're familiar with C, and all of you should be familiar, then you should be able to look at a Verilog code and sort of at least figure out what's going on just from the C, just because you're familiar with C. VHDL actually grew as a project in the Department of Defense in the States a few tens of years ago. It's based on a different programming language called EDA. I don't know if anybody heard about this programming language. If you didn't, that's good for you because it's not something you want to be familiar with. But this is how the VHDL stream grew. Verilog actually started as a simulation language. It didn't start as a hardware description language, but with time it evolved to being an actual design language and slowly became the standard out there, together with VHDL. There's a rumor that, which I haven't verified, that Verilog is more popular in the States, where VHDL is more popular in Europe. At the end of the day, when you go out to the industry and you get a job, then your company will probably impose one or the other. The good news is that once you know one of the languages, it's not going to be a problem transporting to the other. It's pretty much coming down to different syntaxes, but the ideas are usually the same between the two languages. So in order not to confuse you, we'll just do one of them and go with that. Now, from now on, I will only show you Verilog stuff. And when I was preparing this lecture, I thought, how do you best teach a programming language? There's really two approaches out there. There's the approach that says, I'll throw as many examples at you, as many programs, sort of tell you what they do, and you sort of figure out from the keywords what's going on and how it's being structured. The other extreme tells you, well, I'll give you all what's called the grammar of the language. I'll tell you exactly, I'll show you the syntax of every single keyword. I'll tell you what it does and how to use it. And then you should figure out how to go about and implement it, obviously with some examples. What I ended up doing, I personally like the second choice, the second approach, give you the syntax, so make it all very formal, so you can have no ambiguity. If you know the grammar or the syntax, then you should, in theory, be able to implement anything you want because you know how to use the language. Obviously, if I just show you the grammar, then you'll have no idea where to start. So the approach in this lecture will be a mixture of some examples, but I will concentrate mostly on the grammar of things. So let's dive straight into it. And here's an example of a structural Verilog description. Remember when we said structural, we said we're describing the circuit, not the behavior of the circuit, but the actual gates or components that we want in there. Now I'll let you stare at it for about 30 seconds to try and figure out what's going on. Now obviously this module there, or this code, implements a decoder because it tells us so. Now, before I actually go and analyze this, I do want to go and formalize what the different keywords are, how do we use the different lines there and what do they mean. Now, as you can see, let me point out the two references here. The one at the top is a reference from the prescribed textbook. The second one is a reference from the Wakerly book, which is also a recommended reading in the course outline. Now, those two books actually take the two different approaches. The prescribed textbook takes the examples approach, and there you go, here's an example, here's an example, here's an example, yada, 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 you figure it out. The Wakerly approach actually goes with the grammar, which I like the Wakerly approach a bit more. You can choose which one you prefer. I think that the Wakerly book is actually better when you come to study Verilog. I made those books available for you at the library. There's a few copies, well, both books, there's a few copies of them. But for each one of them, there's at least one copy in the Open Reserve or My Course or whatever they call it these days, because they keep changing the name. You know, the place where you can only check it out for 2 hours and you have to sit there, but you can check it out. I don't know what they call it these days. So there should always be a copy of the book if you do want to refer to it. That's not what I wanted. There we go. So let's talk about the syntax of Verilog. So for a starter, the Verilog compiler is very similar to C. It ignores most white spaces and line breaks. I don't know how many of you are actually aware that when you compile a C code, and that's a similar thing with Verilog, the compiler will pretty much, the first iteration on your code, it will dump out any white spaces and line breaks. Therefore, you can break a line in the middle as long as you didn't put the semicolon at the end. You can put as many spaces as you want. The compiler will just ignore it. Same story with Verilog. And then just like C, you can have comments that are either single line comments with a double slash, or if you want a block of comments, just like in C, you start with a slash star and end it with a star slash, similar to C. Now, as any other programming language, Verilog gives you some reserved keywords, and these are, in a way, the commands or the instructions you can put into Verilog. In the example over there, everything that's in green are the reserved keywords, and that's the convention I will use throughout this lecture. Anything that's green is going to be a reserved Verilog keyword. Anything else is stuff that either identifiers or things that we came up with. So in this example, you have keywords like module, input, output, wire, not, end, and end module. You can find them all in green over there. Other than the reserved keywords, there's the user-defined identifiers, which are things like variable names, register names, parameters, wire names, input, outputs, anything that we want to give names to or need to give names to are user-defined identifiers. Similar, I'm not sure if that's identical to C, but those identifiers must start with a letter or an underscore, and then they contain letters, digits, underscore, and dollar signs. Anything else is illegal. The compiler will yell at you if you try that. One of the main differences between Verilog and C and many other programming languages is that all the keywords or identifiers are case sensitive. If you write something with, say, first capital letter and then everything else in small, is not the same as writing everything else in capital or everything else in small letters. Verilog will treat them as two different things, and this is something you really have to watch out for, because this is really easy mistake to do and really hard to find because you don't think about this. So keep that in mind. Everything is case sensitive. Make sure you're consistent throughout your code. Now, and this is where it gets interesting, the actual grammar. Every Verilog code starts with a module declaration. A module, if you want, is one of those black boxes. It's whatever is enclosed in it. And you can assign for every module the inputs, the outputs, and the functionality of this module. Now, and you can always compare it with what's going on there. Very formally, a module will start with the keyword module. It will have a module name that you can later instantiate this module with. It will have a list of port names. Port names mean it's either inputs or outputs, or there's also a special port that's in-out, a bidirectional input or output. We don't worry too much about it for now. That will be followed inside the module with all the input declarations or the output declarations to define which ones of the ports are inputs and which ones are outputs. We'll define net declarations, which will be things like internal wires in the module, and of course I'll go one by one and I'll explain it in more details. It will follow by variable declarations, so you can have integer registers. We'll talk about what variables are. You can have parameter declarations, constants, we call them parameters. And then the bulk of the code will be the concurrent statements. So as you can see, it said statements. You can have one or more. And this is where the majority of the code goes. So everything, the bulk of the code that you see there, these are the concurrent statements. And again, I will expand more about each one of those lines here. Now, when we define a module, we do define a black box like this. Then once you actually write a module, and you tested it, you know that it works, you can then forget about all what's going on inside. All you care about is the interface to your module. So what the inputs are, what the outputs are, and and what does this module do? Similar to a black box, and this is the way I want you to think about it. That any module that you write is a black box that you can then later connect to other black boxes or to other gates if you want. Now, just a convention, although you don't have to, every one of those modules, it's a convention to put every module in a single file of its own. Verilog will allow you to put more than one module per file, but just Verilog programmers sort of out there decided that it makes things neater if every module gets its own file. You don't have to, but please do. No, let's hope it doesn't crash anytime. All right, so now we'll go through a few of those things there in the module declaration, what can actually go inside your module. We start off with the input and output declarations. So for each one of the ports that you define there, you have to define whether it's an incoming signal or outgoing signal, input or output. As I said, there's another one called in-out. Don't worry about it for now. The way we define them, we can either have the word either input or output, let's say input, followed by all the identifiers, so all the port names that we have up in the module, and this will define that these port names are in fact inputs to our module. You can have one line of input with a list of all the identifiers, Or you can break it into few lines of input. So you can have input, one identifier, next line. Input, another identifier, and you can have as many as you want. It's usually a convention to break them down into things that make sense. You might have few inputs that are related to each other, so you put them in one line. Then another group of inputs are related to each other, put them in another line. And this is same case for output, so same story. Now, one thing to remember, input signals can only be read. You can't write out to an input signal, which makes sense because it's an input. What may not make so much sense is that output signals can only be written to. You can only, if you're sending something on an output, you can't go back within your program and check what that thing was, unless you define this output as a register variable, which is something we'll talk about on Tuesday. But if it's not defined as a reg, then you can't read that output back in your program. Then again, if you wrote something to this output, you should probably have another way of figuring out what you just wrote there. So if you look back at the module declaration there, so we said what input and output declarations are. And again, it says declarations, as in it can be one or a few lines. And that's true for any one of those lines there. The next thing is a net declaration. Nets are pretty much, you can think about them as wires. Net, wire, same thing. We will, in fact, in this course, only talk about nets of type wire that will use the keyword wire. There are different types of nets, but they're not used very much. You can have a net that would be, say, a supply 0, supply 1. So it's a wire that's always connected to a voltage source. You can have a net that incorporates in it a three-state methods. You can sort of turn on and off the net. Again, we don't concentrate about these too much. Let's think about nets as wire for now. Now, wires are things like your input and outputs. When they come in, they are wires. If you want to connect different components, and I'll go back to the example before, you can see that we're connecting them using wires. When you define inputs and outputs, they will already by default be defined as wires. If you want any additional wires in your module, you will have to declare them with this keyword wire. And a lot of the things I say here are still not quite clear because we don't see examples. I will show you more examples and you'll see what we can do with wires and input and outputs and all these other things. One of the things I sort of didn't talk about before with input and output, and you can see it here, is this syntax of a vector syntax. Obviously, MSB and LSB stand for most significant bit and least significant bit. We'll come up to talking about them in a few minutes. So leave it at that for now. If you don't define them as vectors, everything should be a one-bit quantity. So a wire with just an identifier will be either a high or a low, not a multi-bit value, or not multiple wires. All right. We will talk about the variable declarations, the parameter declarations on Tuesday. I do want to talk about the concurrent statements now. Concurrent statements are, as I said, the bulk of your code. In the example that we had before, we had, and I'll put it back up in a second, we'll go back and analyze it. We had AND and NOT gates. We instantiated AND and NOT gates, and these are what we called components. So a component is just one of few concurrent statements. When we have a component, we instantiate this component. It's pretty much like designing in your schematic. Take either a gate or a black box, put in your schematics. That's what we call instantiating this component. Now, there's a very formal syntax to how you go about doing this. You will put the component name here, whether it's a AND or a gate, or if it's one of the modules that you wrote, you will write the module name here. For each one of those components, you have to give it an instance identifier. You have to give this particular instance its own unique ID. And the reason for this is if you think about a circuit that have 8 different AND gates, so each one of the AND gates will be called just an AND, that's the component name, but I will give each one of them a different name. Now, it's important to give them different names because if you have, say, a mistake somewhere, you screwed something up, and the compiler needs to give you an error message, it's better off if they tell you, hey, you screwed up in AND gate number 5, which is the instance identifier, rather than there's a problem with your AND gate. If you have 80, you can still figure it out. If you have 8,000 gates, then go figure out which one of them is the problematic one. That will be followed by all the signals that are going into your module. If you remember when we defined the module, we defined the port names, the input and the outputs. This is where you connect signals to them. This is when you say the first port there will be connected to this first expression there. And it's an expression rather than just a signal name, because you can actually put complex expression. You can evaluate something up there. In the simplest case, just think about it as connecting signals into your port. Now, again, we'll see examples. As I said, components can be other Verilog modules. They can be library modules, things that come, say, in your design tools. Xilinx have a lot of different modules. You've seen them when you worked in the lab. And it can be those built-in gate types, and or not, and so on. Now, let me put back the example over there. Now, in the example, you can see we instantiated the components NOT and AND, which are just the built-in Verilog gates. You can, now that the example is back up there, you can see that I'm following the component name with the instant name, and usually I just chose to call them G for gate, and then N for NOT, A for AND, followed by the signals that are connected to them. Now, with those built-in gates, we have the obvious gates that we know. We can either use AND or NOT. We can have XOR, and then NAND, NOR, XNOR, and then a buffer, which just pretty much, well, we talked about buffers. These are all reserved keywords in Verilog. They're already there. You don't have to re-implement them. They will just instantiate the gate as you think about it. Most of them can have, with the exception of the obvious ones, they can have as many inputs as you want. So you can have an AND gate with, say, 5 different inputs. For all the built-in gates, they will always have the ports order as the first port is always the output, followed by as many inputs as you want. So in a way, that's good because we don't know how many inputs when we write in the AND gate. We can just write AND, one output, and then followed by as many inputs as we want. And you can see this again in the example out there. You have the gate, you have the instant name. The first signal name is the output, followed by, and then in the AND gate, in the AND cases, we have 2 inputs. In the NOT, the inverter, we have 1 output followed by 1 input, which is obviously you can only have 1 input per inverter. Now that we, I introduced a whole lot of grammar, we could go, would that work? Back to the example and now see actually what's going on here. Well, I said we're implementing this decoder. The decoder, as we know, will have, and it's a decoder with an enable signal, so we'll have the enable signal, the two A1 and A0 input signals, and it will have the four outputs, D0 to D3 outputs. So in terms of port names, so this is, I've got the module name, which is just a descriptive name, decoder 2 to 4, I don't know what ST stands for. This module will have all the different ports, enable, A1, A0, and all the Ds. We then later say, well, EN, A0, and A1 are going to be my inputs, D0 to D3 are going to be my outputs that are automatically defined as wires, and you can, now that you have the schematic here, you can actually see those wires. But we will need some additional wires to connect the different gates between themselves. So for example, this inverter here needs this wire to connect to the next gate. The outputs from these AND gates need wires to connect them to the next AND gate. So there's some additional wires that are not actually either the inputs or the outputs. So we have to define them in this line here. And then we start writing everything out. And you can, when you have the circuit here, you can pretty much see one-to-one what's connected how. We'll start off with assuming we only have A0 and A1, we don't have their inverted versions. We have to create the inverted versions, which is this wire here and this wire here. And these will be these two NOT gates, the two inverters, this one and this one. So we will take, for one of them, A0 as the input. Spit out A0 underscore N. Underscore N, by the way, when you see it, it's a bit of a convention for the negation of a signal. And this will be this wire here, A0 underscore N. Similar, this inverter here will take A1, and this would be my A1 underscore N wire. Then the next four AND gates will correspond to this first level of AND gates. Remember, we said we write out the output as the first signal, so N0, N1, 2, and 3 are going to be the output wires, which will be this one, this one, this one, and this one, where each one of them will take a different combinations of inputs. The first AND gate will take the two, not A0, not A1. So this one here will take not A0 and then not A1. The other three will take the other combinations, so we want to cover all the possible combinations in a decoder. And it will connect them to outputs of those AND gates called N0 to N3. So net 0 to net 3, which are those four wires there. In the next step, we want to take our AND gates here and connect them all to the enable signal. So these are all these enables here. And each one is connected to a different one of the wires that came out from the first level of ANDs. And this will in turn be connected to the outputs that were defined up here. Now, one of the main things to realize, I mean, I'm pretty sure everyone's sort of been able to follow what's going on. It's not that complicated. But what happens if I took away this circuit and just gave you the description? Question? No. No? All right. If I didn't show you the circuit and just gave you the description, are you able to then reproduce this circuit? No. In theory, will you be able to reproduce the circuit? Not you specifically. I mean, this code here gives us enough information to come up with this structure here. What will probably happen when you're given a code like this and you want to draw the corresponding circuit is that you'll probably, because you don't know what the final result should look like, you'll throw the gates anywhere, you'll start connecting things everywhere, and you'll have a very messy circuit. But, assuming you did connect all the right signals, it will look messy, but it should be correct. And then you can go and tidy things up, because now you realize what the circuit needs to do, and make it look pretty. I will give you some other examples where, especially in tutorials, where I'll just give you the code and I'll tell you, well, draw the circuit, and this is exactly what you're going to have to do. In tutorials, it might not be obvious what the end product is going to be, and then you start off with pretty much, you look at the first line, okay, it's an inverter, input A0, which is an input, output A0N, which is a wire. Then you draw an inverter, put A0 here, A0N, and just let it, leave it floating until you see somewhere else that uses this signal A0 inverted, and then you start connecting them together. So what I'm trying to say, don't feel bad if you see a description and you end up with a really messy circuit. This is how it happens. Obviously, when you program those things, if you write a structural description, you know what circuit you're trying to implement. So you will go from a circuit into a description. The computer software will be able to connect everything for you nicely, no problem there. All right. So far, are there any questions? How many people lost me along the way? It's going to get much more interesting in this. So far, we just implement things. Chris?
Sorry, what's the point of the wire? Can't you just take the output and show that against the
Well, the question was, what was the point of the wires? Well, if you didn't have wires, that's the dumb end. So if you didn't have wires, then nothing would be connected together. Why do we have to actually declare them? Which one is the others? The input and the outputs, you mean? Well, if you go a couple of slides back, input and outputs are wires by default. You don't need to declare them. You could. You could if you wanted to. If they're not wires, because I said there's different types of nets. If they're not of type wire, you can override this default statement and actually define them as something else. We will see, by the way, that we will, on Tuesday, override a few of those inputs or outputs, and well, the outputs usually, and make them registers rather than wires. But for now, if you don't declare anything else, they are wires. All right. Not done yet. There's no, I'll go through. You're welcome to go, but. Here's another example. Now, in this example, obviously, the title here tells you it's going to be a multiplexer. The module name tells you, and the comment, everything points out toward the multiplexer. I'll be very disappointed if it wasn't a multiplexer now. So you know what you're expecting to see here. And this is a structural description of a multiplexer. Now, there's not that many new things around here. I mean, you got your inputs, your outputs, your wires, and your NOT and then OR gates. The one main difference from what we've done before is now we have this vector notation here, and you can start seeing that we're referring into individual signals in the vector. So just formalizing a little bit of what vectors are. If you remember in week 4, we said for convenience we can group together a number of related signals into what we call a bus or a vector. We had this notation. I should get my pen back. We had this notation of a thick wire that had a stroke through it and a number to tell you how many signals are actually going on this bus. Now, in Verilog, when you want to define a vector or a bus, we'll call it vectors, then the syntax is in square brackets where you put your most significant bit on the left and the least significant bit on the right. Now, if you look at the example there, have a look at how I define the input I, which is obviously a 4 bits vector. Most significant bit is 3, least significant bit is 0. And look at then the wires D and N that are defined as the most significant bit 0 and the most significant bit 0, the least significant bit 3. So I swapped the order. By the way, this is intentional in this example because I wanted to show you something. Now, when we define or refer to a vector, the terms most significant bit and least significant bit should be thought of as the most significant bit is the bit on the left-hand side, leftmost bit. The least significant bit is the rightmost bit. But you can decide which one of them you want to have where. So for example, I might define my vector as being, where, in the regular notation that we that we worked with, 3 is the most significant bit, 0 is the least significant bit, and you can refer to it that way. I can also define my vector to have 3 as the least significant bit, and 0 is the most significant bit. Now, why would I want to choose one or the other? Well, depending on what you're actually trying to implement. You might want to say the leftmost bit is bit 0. I will refer to it as bit 0. Or you can say, use the standard convention and say the leftmost bit is 3, rightmost is 0. It essentially doesn't really matter if you're consistent throughout your program and you know what bit you're actually trying to refer to. If you start mixing the two conventions up, this is when you start getting code all over the place. By the way, you don't have to start at 0. You could say, I want my vector to be defined as bits 5, 6, 7, and 8. And have a vector that doesn't actually have bits 0 to 4 or something above 8, but you will be able to refer to these individual bits there. Now, in order to refer to actual individual bits, you can just, similar to C, just write the index name inside the square brackets when you're working with the signal. So for example here, I do have, and let's have a look at, where's my, there you go. I do have an input I, which is now a 4-bit input with input I3 as the most significant bit. It will make this 1, 2, 3, and this is the bus of the vector I. And then in my implementation, I can then refer to individual bits. So when I have I1, obviously I will only talk about this bit there, and so on and so on. You could refer to more than one bit at a time. You can have a subset. If you wanted a vector that consisting of those 2 bits, you could have something that looks like I 2, 1, and it will go to your vector and then pull out just those 2 bits there. So just something you can do. So to summarize it, you can refer to a single bit, you can refer to a subset of your vector, or you can refer to the whole vector. If you want to refer to the whole vector, you can just say either I, which will refer to the whole vector there, or if you want to be explicit about it, you can also refer to it with the indices when you work with them. I think we'll stop here for now. Please, before next lecture, just have a look at this example, see if you understand what's going on there, and we'll continue on Tuesday.